To prove this claim, remember we start with an x, which is h plus this linear combination of E sub ij's. So let me copy this assumption down in here. Remember, this part can be assumed to be non-zero by our hypothesis in this second case, that the ideal A is not contained in H. So there could be some non-zero part outside of the H. To prove this claim, we consider the following two sets of roots. The first set is delta negative. This is a collection of E sub I minus E sub j's, where I is greater than j, and the coefficient for E sub ij, which is C sub ij, is non-zero. And delta plus, which is a set of roots E sub I minus E sub j, where I is less than j and C sub ij is non-zero. Namely, for this first set, delta negative, we are considering the negative roots. This is a negative root, where the coefficient before E sub ij is non-zero. And this is a set of positive roots, such that the coefficient C sub ij is non-zero. I hope you guys still remember the definition for the positivity of roots. Being positive means the first non-zero coefficient of E sub I is positive. So in this case, it is positive, plus 1. And in this case, the first non-zero coefficient is negative 1, because j is less than I. The quick observations about delta negative and delta plus are the following. First, both delta negative and delta plus are finite subsets of delta. This is obvious. And at least one of them is non-empty. Using notation, we can write this as delta negative union delta plus is non-empty. This part follows from the fact that X is not in H. And as a result, there must be at least one C sub ij that is non-zero, which will make the corresponding delta negative or delta plus to be non-empty. And based on this observation, there will be two cases to consider. The case when delta negative is non-empty, or the case when delta negative is non-empty, and the case when delta plus is non-empty. And as you can imagine, by symmetry, it suffices to just prove one case, say when delta negative is non-empty. So let me write this down. There will be two subcases of the case number 2. Subcase 2.1, if delta negative is non-empty. And now let me recall one thing. Recall that there's a partial order on the space of linear functionals on H0 star, which gives a total order on the set of roots delta. Here we listed all the positive elements in delta. And similarly, you can list all the negative roots after 0. So this order is actually a total order on delta. Namely, every two roots are comparable. So recall that there exists a total order denoted. Remember previously we used a greater sign, but here we are going to use the less than sign. Defined on the set of roots delta. Remember this is a superset of this delta negative. I should emphasize that this means every two elements in delta are comparable. Now, because this delta negative is non-empty, let E sub I minus E sub j be the smallest element in delta negative with respect to this less than relation, this total order. This is possible because delta negative is non-empty and finite. So we can choose the smallest element. For this subcase 2.1, we'll prove that E sub in is in A. And as you can imagine, for another subcase, namely when delta plus is non-empty, we'll prove symmetrically that E sub n1 is in A. To prove this, we're going to use our Lie bracket manipulation trick again. In fact, we're going to use the following subclave. We'll show that this iterated Lie bracket E sub 1i, comma, the Lie bracket of x, comma, E sub jn is a non-zero multiple of E sub 1n. Okay, now let's get started with this. The first thing we do is that we're going to just plug in the definition for x. Since I and j are already appearing here, we're going to use pq as our index for this sum. And we'll break down this sum. First, we're going to single out this h. The first part is E sub 1i, comma, the Lie bracket of h and E sub j. And the second part is this complicated sum. We're going to use the bilinearity to pull the constant out. The sum of C sub pq times this iterated Lie bracket. And the next thing we do is that we are going to explicitly write out this Lie bracket using its definition. This is equal to EPQ times EJN minus EJN times EPQ. And we are going to separate those two parts. We will end up getting 3 parts. The first part is just this guy. And the second part is this. And the third part is this thing. We'll give them labels. So triangle number 1, triangle number 2, and the triangle number 3. The part number 1 is easy. So triangle number 1 will just be equal to E sub 1I, comma, remember this part, by our computation at the beginning, is equal to E sub j minus E sub n applied to h times E sub jn. This is a scalar, which is equal to just 0. This is because if you look at this bracket, if you pull out this constant outside, I, on one hand, I is not equal to j. So the matrix E sub 1I times E sub jn is equal to 0. On the other hand, because n is not equal to 1, so E sub jn times E sub 1I is also equal to 0. So it follows that this Lie bracket is equal to 0. Now how about the second guy? The second guy is also easy. This is equal to, if you just use the definition for this Lie bracket, this is E1I times EPQ times EJN minus the multiplication in the other way. And this part vanishes because here n is not equal to 1. And it's greater or equal to 2. In particular, not equal to 1. But this part could be non-zero, because if P is equal to I, while Q is equal to J, then the product of those three things will be equal to E sub 1n by the matrix multiplication. That case could happen because the sum ranges over all PQs where P is not equal to Q. And this first part will have a non-zero term, which is the case when P is equal to I and Q is equal to J, times, in which case this product of three things will be just E sub 1n. So here you have to remember that C sub ij is non-zero by our choice of ij. We chose ij so that E sub I minus E sub j is the smallest element in delta negative. And by our construction, delta negative consists of exactly those E sub I minus E sub j's, where I greater than j, such that C sub ij is non-zero. So C sub ij here is non-zero. And now let's look at the third part. The third part is equal to, now as before, we're gonna use the definition of this Lie bracket. This will be equal to e sub 1i times e sub jn times e sub pq minus the product in the other way. The first part must vanish, no matter how you choose p and q, because here we assume that I is not equal to j. But the second part could be non-zero. It is non-zero if and only if p is equal to n and q is equal to I. So in the end, you will reduce this sum into just c sub n1 times e sub ji. And at this point, let me remind you the thing we want to prove. For this subclaim, we want to prove that this thing is a non-zero multiple of e sub 1n. Namely, we want to prove 1 plus 2 plus 3 is a non-zero multiple of e sub 1n. This thing is good. This is a non-zero multiple of e sub 1n. But this guy could be a little bit annoying. And now let's see how to deal with this part. There will be two cases to consider for part 3. Case 1. If here the pair I, j is equal to n, 1, then this cn1 times eji will be equal to cn1 e1n, which is equal to, because now n is equal to I and 1 is equal to j, this is Cij times E1n, which is precisely what we concluded for the part 2. So this will be equal to the part 2. And in this case, the thing we started with, which is equal to 1 plus 2 plus 3, and remember 1 is always 0. So this is equal to 1 plus 2 plus 3, and 1 is equal to 0, but 2 plus 3 will be twice of 2. In this case, I should use another color for this. This is twice of c sub ij times e sub 1n. But this coefficient is non-zero, because we assumed at the beginning that c sub ij is non-zero. That is how we chose the pair ij. And because C is the field of characteristic 0, twice of this non-zero number must also be non-zero. Anyway, we conclude that this guy is a non-zero multiple of e sub 1n. Now, as a second case, we're going to consider if I, j is not equal to n, 1. In this case, this e sub ji will not be equal to e sub 1n. And we really hope that this constant c sub n1 could be equal to 0, so that this term will also vanish, so that the only term that is left for us will be the part 2. And this is indeed the case. Because if ij is not equal to n1, then remember our total order on the set of roots. En minus e1 will be less than ei minus ej. Just by definition, if you move this guy to the right hand side, this is e1 plus blah blah blah. And the coefficient of e1, when you move this to the right hand side, will be plus 1. So the thing you get will be greater than 0. So you have this inequality. However, by our choice of ij, how did we choose the pair I, j? We chose the pair I, j so that e sub I minus e sub j is the smallest element in delta negative. However, if ij is not equal to n1, there is a term en minus e1 is strictly less than ei minus ej. We chose the pair I, j so that ei minus ej is the smallest element in delta negative. And remember, the set delta negative consists of all the roots that are negative and the coefficients e sub ij is not equal to 0 for the corresponding the pair I, j. So, if there's another term, en minus e1, that is strictly less than this guy, which is supposed to be the minimum such that the corresponding coefficient is non-zero, it follows that the coefficient corresponding to this guy, which is c sub n1, must be 0. So, in this case, we have this guy is equal to just the part 2, which is c sub ij times e1n, a non-zero multiple of e sub 1n. And this finished our proof of the subclaim, namely this subclaim. Once this is proved, we are done, because by our assumption, x is in A. And remember, A is an ideal, so this iterated Lie bracket will be in A by the definition of ideals. And this subclaim will imply that e sub 1n is in A. And this is the end of our proof of this claim under the subcase that delta negative is non-empty. And I mentioned before, for the case when delta plus is non-empty, the proof is very similar. Let me just quickly mention which parts we need to change. We need to take E sub I minus E sub j as the largest element in delta plus. And in the end, we will prove E sub n1 is in A. Previously, we proved E sub 1n is in A for the case when delta negative is non-empty. And this completes the proof of this claim, finally. And remember, once this claim is verified, we are done. Parallel reasoning at the very beginning. We have already shown that this claim will imply that A is equal to G. Under the case number 2. Remember, the case number 1 was already addressed at the beginning. So this finally finishes the proof that SLNC is simple over C for n greater or equal to 2. So we are done.